Hello everyone, welcome to our next installment of Introduction to Remote Sensing. We're still on the topic of classification today, and we'll be moving on to the accuracy assessment component. My name is Shaun Levick from the Geospatial Ecology and Remote Sensing Lab, and for today's exercise we will again be making use of the SNAP toolbox. That is the Sentinel application toolbox from the European Space Agency, and it's a platform which is a compilation of different toolboxes for downloading and analyzing Sentinel-1, 2 and 3 data. For today's exercise we'll be using our Worldview 2 image collected over Darwin, which I've loaded up in the Product Explorer. Remember, you can easily open that just by going File, Open Product, and choosing the Darwin file from our course folder. And in our last exercise we also classified the image. Let's just open it up to have a look at it. Open RGB image window and click OK, and you will see the image of Darwin coming up on the screen in true color. You'll see a number of vector overlays on the image. That's from the work we did last time. We can hide those overlays by using this icon up here. Those were the training areas that we used for our supervised classification. So just familiarize yourself with the scene again, and remember that in the last exercise, the previous video of the sequence, we conducted a random forest supervised classification, and I've loaded that up here again as product number 2. And as we look through these bands, as we come down to the folder bands, we'll see we have labeled classes. I'm just going to double click that to open it up again, and here we have the classification that we performed on this image using 7 different land cover types: water, mangrove, dense vegetation, savanna, sports fields, buildings, tarmac or bitumen, and bare soil. Now, we created this random forest classification from training data that we collected on screen, but in order to really use this type of thematic map in any ecological study, we need to be very aware of the accuracy of our classification and be aware of any errors that have crept in, and also to know which land cover classes we're able to classify with greater confidence. So in order to do that, we need to construct an error matrix. So in addition to having training data for generating this classification, we also need to make use of validation data. And it's very important that this validation data is independent of the training data. Otherwise, we would have bias in our results. Now, we can obtain this validation data from a number of sources. In the past, they would often have come from fieldwork, collecting data on ground in the field. And that's often a very good solution. But also with the very high resolution optical imagery that we have available today, expert users can also collect this type of data on screen. So for example, we could collect validation data using the base maps in Google Earth. We could use drone imagery, but for the exercise today we're going to stay within the SNAP environment, and I'm going to show you how to use the pin feature for deriving validation data that we can use to construct an error matrix. So let's just go back, click on the tab in the top, go back to our true color image. What we're going to do is zoom in, go to our navigation, let's zoom into the pixel level. Lovely image this, Worldview 2 satellite. Remember that with the left click, grabbing the window in the navigation pane, we can move around. And what we're going to do now is very similar to collecting the validation, the training data sets. we're going to collect some validation data. Ideally, this would be completely independent. We'd get a different operator to collect this, or you would collect the validation data prior to running the classification. But for today's exercise, we're just going to run with collecting the validation data on screen right now. So we'll be making use of the pin tool, and that's right up here in the top toolbar. So we have the selection arrow, hand for navigating, magnifying glass. The next one in the list is the pin placing tool. We used this earlier when looking at spectral profiles. So making sure that you have selected the original image, product number 1 in the Product Explorer. Then click on the pin placing tool, and we're going to collect, for the purpose of the exercise today, we're just going to collect 10 samples per class. Ideally, we would use 30 to 50 samples per class to create a robust validation data set. For today's exercise, we'll just be collecting 10. And it's very easy to place pins. You simply use a left click, and we place a pin in the ocean, and we can move around the image, placing pins in water bodies. Ideally, these should be distributed throughout the scene. So we'll place 10 of these in our image. Now, those pins are now placed in pixels that we know represent water. So we want to be very sure of the land cover class that we're placing these pins in. What I'd like you to do next is move up to the top toolbar, click View Tool Windows, and come down to the Pin Manager. This will bring up this dialog box in the bottom here. You can make that as much as half of your page. You'll see that we now have an X and a Y coordinate. That's the pixel location within the image. We have a longitude, latitude coordinate for each pin, and there's a default color added to each pin and a label. Currently, these are labeled pin numbers 1 through to 10. We're going to rename these to represent the land cover class we're interested in this case, water. So we can modify these with a double click and simply type water. Unfortunately, I haven't found a way to quickly copy this down the table. So what I suggest you do is just double click, highlight water, use Control, Command C, Control or Command V to paste that into subsequent lines. So I'm going to copy that and just quickly paste that through the rest of the list. If anyone finds a shortcut for doing this, please let me know. But now we have our 10 pins labeled as water. If you don't remember the classes that you used in your classification last week, just click back on your, if we go back to the labeled classes tab and click on the color manipulation tab, it gives us some good information. It shows us the frequency of occurrence within the scene, and it also reminds us of, it provides a legend for the classes we used. So we classified water, the next on our list was mangroves. So let's go back to our image here, and let's place 10 pins in mangrove areas now. For doing that, let's go back to the pixel view and go to an area where we know we have a lot of mangroves. Go back to the pin placing tool, and let's place 10 pins in areas that we know are definitely mangroves. Let's move to an area here. So we have another 10 pins, and you can see that they are populated down the list here. If you'd like to, you can change the color. It doesn't have any major influence though. What's more important is to rename them to something meaningful. So let's call that mangroves. Again, we just copy that, paste it through the rest of our list. And let's have a look at our broader scene again. Mangroves, there we go. We've got 20 pins placed across our image now. Let's do buildings next. Zoom in to the pixel level. Let's go over an industrial area and collect a heap of buildings. Remember to distribute this throughout the scene. So we'll move over to the city and collect a few more until we have another 10 pins laid out. And remember, we're just using 10 as an example now. For a robust validation, you would want a higher sample number. Same procedure. Copy that down. And then we're ready for our next land cover class, which was, let's see, we could do bare soil or savanna. Let's do sports fields next. So lots of sports fields in Darwin, cricket grounds, golf courses. So check that our pin placing tool is highlighted. And let's grab some samples from these different sports fields, ensuring that they are distributed throughout the image. There we go. We have another 10. Sports field. Copy that. Paste it down the list. And there we go. So now we've done 4 classes. I'm not going to do the remaining 3 right now. I'll rather just show you what we're going to do with these, but you can continue in your own time to collect 10 more pins for the remaining land cover classes, which are bare soil, tarmac, and savanna, dense vegetation. So we actually had 8 classes. Okay, moving back to our image. What you'll see here is we have all these pins placed in our image over Darwin. We have the X, Y, long lat coordinates. If we want to save these pins, we can export them to an XML file. That means we can then load them up again at a later stage. And we would bring them back in another image by using this import tool. We can also export them as a text file, CSV format. Now, it's great that we have collected these pins on our true color composite image, but what we're actually wanting to do is validate the classification that we produced last week, which is over here. And as you can see, when we move to this image, there are no pins available. And that's because these pins are stored in the vector data folder relating to a particular image. See, we have pins here. If we come down to the vector data folder for the classified image, the random forest image, we also have pins, but there's none in our table. So let's go back to our true color image where we have created the pins, and then have a look at this icon on the right hand side. Transfer the selected pins to other products. If we click that, we then have the option of copying these pins to another product. So if we tick that and say OK, now when we move back to sorry, I made a mistake there in that if you look at this again, it says transfer the selected pins to other products. As I only had one pin selected, it's only copied one pin to our classified image. So let's go back here. What we need to do is highlight all of these pins. Now say transfer to our Darwin random forest image. Say OK, update, yes. And now when we go back here, we have these pins placed across the image. Just notice that one of these pins, pin number 40, doesn't have a proper label yet. That should be sports field. Okay, and there we have it. We now have these pins overlaid on our classification. Now, how is this useful to us? Well, we have a classification which was derived from a supervised random forest approach. And in this column here now, in the label column, this is independent validation data. And if we want to compare this validation data to the actual classification, we can query the pixel locations of each pin and see what it was actually classified as. Now, in order to do that, we're going to make use of this filter pixel data tool. So this little funnel allows us to set what data is displayed in this table. So I'd like you to click that, and what you'll see is brings up the bands that are available within a particular image. And currently we're not displaying any information from the bands in the pin manager. But if we click on labeled classes, this will now bring up the value of the labeled classes for each pin location. So let's say OK and see what happens. Now, these labeled classes are numbered from 0 through to 5. And in order to understand what these numbers mean, we need to move over to the color manipulation tab. We'll see that water, our classified water, had a raster value of 0. Remember that the classification produces a raster of different numbers, and each number relates to a specific class. So in our classification, our category water has the value of 0. So what that means is that if we look down this list, and if I just click here to order it alphabetically by the labels, let's look at the bottom here at our water categories. These values of 0 represent our random forest classification, and these labels of water are our validation data. So we have a very good match. We actually have 100% accuracy based on this validation data. If we look at buildings, label class 5, we come over here, we can see that buildings did have a value of 5, and each pin is matching the corresponding raster value. That means, again, we had very good success in classifying buildings. If we come to mangroves, however, our mangroves in our classification had a value of 1. So that means we did very well, but there was one instance where our classified result classified an area as savanna, but our validation data say that it is actually a mangrove. So for this set of 10 pins for the land cover type mangroves, we only got 9 out of 10 correct, so 90% accuracy. We have a few problems with sports field 2, in that sports fields should have a value of 4 to be correct. We have one instance where we classified a sports field as 5 as a building, and another with no value, and that means it wasn't classified in our previous classification. So all in all, that's a pretty good result. To be thorough with this, what we need to do is, of course, add the extra pins to this table for the remaining land cover types, and then we can export this whole table to a text file and open it up in a spreadsheet. And then we then have the tools that we need to construct the error matrix. Remember that the error matrix, we compare the validation data to the actual classified data, and all we need for doing that is the information in these two columns. This column providing the validation data, and this column providing the classification results. Once we have that, we can generate the confusion matrix or the error matrix, work out our producers and users accuracies, our overall accuracy, and calculate the kappa coefficient. So that's all I wanted to show you today, and this is the last piece that you need for completing your next assignment, and look forward to seeing you all next week. Thanks very much. Cheers.